Now we will discuss about the parallel plate capacitor and we'll try to derive the capacitance for a parallel plate capacitor. Now first let's see what is a parallel plate capacitor. First case, we will try to see a parallel plate capacitor without any dielectric medium and we'll try to find its capacitance, and then we will move for a capacitor with a dielectric medium. So first let's see what is a parallel plate capacitor. It's a capacitor with two metallic plates and they are suppose of area A. This is first one, this is second one. They have the similar area of these plates, which is A, and they have a distance between them which is small d. Let's suppose. In the first case, we are not taking any particular dielectric media inside. So let's suppose it is filled with air. Therefore, this capacitor is called a parallel plate capacitor, where the two metallic plates are parallelly, they are sandwiched with a dielectric and they are parallel to each other. So, as we know that this is a capacitor, generally the capacitor, as we know, is the two conductors sandwiched with a dielectric medium. Here we have taken dielectric medium as air. So, at the beginning, let's suppose we give it the charge Q, and this is suppose plus Q and this is minus Q, right? So next we know that the surface charge in this plate would be equal to charge per area. The surface charge is calculated as the charge, the total charge divided by the total area. So this is the surface charge for the first plate as well as the second plate, as they have the similar charge and the same area. So coming to the calculation of the capacitance of such plate. So we know that sigma is Q by A, and since the distance between these two plates D, we imagine it as to be a very small distance. Therefore, we can imagine these plates as the infinite sheet holding a charge Q. An infinite plane sheet, we already know the electric field per sheet for the sheet would be sigma by 2 into epsilon, where epsilon is the permittivity and K, dielectric constant for the air, is 1. So sigma is sigma electric field for this plate is sigma by 2 epsilon naught, which is the electric field for a infinite plane long sheet, which we have already studied. Also for this plate we calculate the second electric field for this plate, which is again sigma by 2 epsilon naught. So therefore, for these two plates, the total electric field becomes E equal to sigma by epsilon naught. So this is the electric field that we find for this parallel plate capacitor. We also know that potential is E into D, or we know that electric field is the gradient of potential, or potential is E into D. Now just substituting this, we get epsilon D, sigma D by epsilon naught. This is the potential for this parallel plate capacitor. Now finally, when we try to calculate the capacitance, now C, we know the capacitance C is Q charge Q by V, which is nothing but Q by sigma D into epsilon naught. sigma epsilon sigma d, and by epsilon naught is V. So this expression becomes Q epsilon naught by sigma d. Now substituting for Q, we know that, or substituting rather for sigma, we know that this expression would be Q epsilon naught. In the place of sigma, we will substitute Q by A. So Q comes here, A goes there, into D. And therefore the final expression becomes A epsilon naught by D. So this is the capacitance for a parallel plate capacitor which has a dielectric medium, air inside, which has a dielectric constant K. Dielectric constant is equal to 1 for air. Now suppose if I have a dielectric medium, if a dielectric media is inserted, suppose there is a dielectric media with a dielectric constant K, then my expression, my whole expression V would become, V is sigma d by epsilon naught K. So since K equal to 1 here, it will be 1 in this place, but as here the dielectric constant we have taken for the material as K, so therefore the potential would be sigma d by epsilon naught K. And finally, if we are going on substituting, we would find the capacitance would be A epsilon naught K by D. So suppose if C is the capacitance without any dielectric medium, or for air. So with a dielectric medium, let's C dash would be the capacitance. Then what we see that with this and this, there is a difference. What is the difference? C dash is nothing but C into K. So as we have increased the dielectric medium, we have induced a dielectric constant here, then the capacitance of the medium, or if we have inserted a dielectric media with a constant K, then the capacitance of this capacitor is also increasing by amount of K. So that's how here C dash is C into K. So for a parallel plate capacitor, we have known that capacitance is A epsilon naught by D, which depends on the area of the plate, the distance between the two plates, and epsilon naught here is the permittivity of this media. Here we have taken air or the vacuum. Now as instead of vacuum, instead of air, if we have inserted a dielectric medium with a dielectric constant K, then the capacitance is increasing K times for this parallel plate capacitor. So with this we have derived the capacitance for a parallel plate capacitor without any dielectric medium, and we have seen that the capacitance depends on the area of the plate of this parallel plate conductors and the distance between the two plates. And as we have inserted a dielectric medium inside, the capacitance has increased K times after inserting a dielectric medium.